our second video about Riemannian optimization. So, what is manifold? How can we imagine an abstract mathematical structure like manifold? And what is it? Actually, we better think about manifold like something real. We cannot describe with mathematical equations or whatever. And the best example I really know, and where you can find a lot of illustrations of how it's working, is just our Earth. So you can think about as a mathematical structure, it's a sphere manifold. But in real world, we don't think about our world like a sphere. It's just an Earth. And you may ask questions about the sphere manifold. And why do we think that our Earth is spherical? Maybe it's just flat, or like people imagined many years ago. And what for? Or is there anything in this mathematical structure that makes our Earth to be spherical? And is it an intrinsic property or an extrinsic? So does the topology of the Earth, this spherical topology, defines that it's actually spherical? The contradiction you may find is imagining a potato and a sphere. And from topology's point of view, they're exactly the same. So they have all the points connected in the same way, and you can transform a sphere into a potato with a smooth transition. So there is nothing special in sphere that makes sphere spherical. And the potato is also sphere in some sense. Another question is how to represent a point on the Earth. So what is Paris? What is Moscow? What is New York? What is the village Tmutarакань in some parts of Russia? How do we numerically represent points on the Earth? And this is not that obvious. So people for many years invented a lot of maps, created atlases that describe our world, to travel by sea, travel by not by sea, and whatsoever. And there are of course different kind of maps, and it was like an atlas, Google Maps. You can imagine some very exotic ones like in the below. So the coordinates look very weird, and there is like no consensus what map should we use. And if you think that, oh, there is a coordinate 1.1 and 2.3, in different maps it's a different point. And whichever map you choose, so you should use the coordinates that only apply to this particular map. And as I said, Spheriness is not something that belongs to the sphere. And if you imagine that there is a constraint that points actually should have norm of 1 in Rn, and that defines the sphere. Actually, in some sense, but it's still not enough to explain why a sphere is so spherical, and why do we say that its curvature is 1, positive. Curvature is not related to this constraint. It's related to something different that we additionally attach to the manifold. For example, we can additionally explain sphere in a different way. So we can pick two angles and describe every point on sphere except some special ones. And in this case, it's not that obvious why should curvature be 1 on every point in this parameterization. And without even knowing what curvature is, we really understand that in this parameterization, it's not that this parameterization is not uniform among sphere. So to explain why Earth is not potato, we need to go a level above to the tangent space, and what curves are, and what speeds are, so on. And on this Earth, you can draw some path, like we travel to Crimea, to the seaside, and our path, our ride by car, can be represented as a function that takes a real number, like the time, and outputs our GPS position. We can normalize our travel path by starting from 0 and ending up at 1 in the Crimea. And in reality, you may pick one of the maps from the above and think it's your GPS that's telling you coordinates where you are. And you can make a connection between your position and GPS coordinate. And your GPS navigator is something that gives you something tangible, like not just position somewhere in Tula, but actual numbers of your coordinates. And that's very important because that's the only way we can work with some abstract math. So we need numbers to put them in a computer. Okay, imagine you're somewhere on Earth, and for example, its coordinates 33 and minus 118. And actually, that's the biggest road system in the world. And that's what your GPS coordinates say. And in reality, you don't need these coordinates to understand that you are there. And we say that this fancy M notation is Earth, is manifold. And what is tangent space is when you're riding a car on the road, you have some velocity, the direction you ride, the speed on your speedometer, and this velocity lies in tangent space at this particular point. So the tangent vector is attached first to this position and is vector, the change of your GPS coordinates given some time period. And the tuple of coordinates themselves and this velocity forms a point from tangent bundle. It's a union of it's a union for points on the manifold and all the possible velocities in every point. It's a disjoint union. So formally, it looks like this. You have a pair of a point and a velocity vector, and they both are points from tangent bundle. This tangent bundle, for example on sphere, is a collection of all unions of all tuples of points and these planes, all points on these planes. Transforming it, we can think as a cylinder. So this cylinder with disconnected strips is the tangent bundle of a circle. This structure can be used in the following way. To get a tangent bundle, you need to create a vector. How do we create a vector? For example, with vector fields, you may think that vector field is just a function that takes a point and gives you a vector at any point on the manifold. For example, you have these vector fields when you differentiate a function. You pick a point and you get the derivative at this point, and that may be a vector valued function too, and it's called vector field. Next, the canonical projection, and this arrow. The canonical projection gives you a point out of the point from tangent bundle. To do that, we just omit the coordinate for velocity vector, and we only appear with the point. Differentiable maps that map you from one manifold to another manifold, like you have a circle and you map all these points from a circle to the plane, and these differentiable maps can be used to transform points from tangent bundle to another tangent bundle to a new space. The question is, how do we compute speed while traveling on Earth? First of all, we need GPS that gives you real numbers, because speed is something real, it's a number, and the clock. Then you give a ride along your route to Crimea and check your GPS specific time. Then you have two observations, and T0 and T1. Then you subtract and compute the average speed while traveling between these 2 points. If the time difference is not that huge, then the estimate is accurate. Yes? Okay. Do we do any assumptions when computing speed? Of course, yes. First of all, we know that we have velocity while traveling at each time. And this velocity belongs to tangent space. And the velocity known is the moment speed. And the way we compute norm is crucial, because we can compute norm in very different ways. And inner product is the way to compute the norm. We take the square root of inner product to get the norm. But what is inner product? Mathematically, inner product is tensor field. This tensor field is actually the same as vector field. And inner product takes two vectors from tangent space and gives you a number. And a function that takes vectors from tangent space and gives a number is called covector. Covector plus vector is scalar. Covector is described with a star. So if you see a star, it's covector. Without a star, it's vector. But what is this tensor field? What is covectors? So what is tangent space and cotangent space? Tangent space is something what we already discussed. It consists of velocity vectors, directions, but cotangent space is not that tangible. For tangent space, think about a function that maps points on manifold on Earth to real numbers, like air temperature. And what is tangent vector? What does it do? Tangent vector is attached to a specific point on Earth and computes the following. It takes a function and outputs the directional derivative of that function at this point. In words, it will compute the change of temperature For example, if we go south, and what is cotangent vector? What does it do? To think about it, imagine a linear functional on TPM, and linear functional outputs real numbers. And also, what you get from loss backward in TensorFlow or PyTorch is a vector from cotangent space. It's not tangent space. Actually, it's cotangent space for a number of reasons. And things happen, and we contradict these two spaces and think that what we get from loss backward is already the most promising direction where our function is changed in the most in the fastest way, but actually not. It's the geometry of the space, Euclidean space, makes these two spaces identical to each other. And the link between differential of f and the tangent space, so what connects the tangent vector and cotangent vector, is the following identity. So v is from tangent space, and df, the differential, is from cotangent space. How can we use tangent vectors and cotangent vectors in the computer? We need real numbers. We need something tangible. Abstract math is useless here. And do you remember these strange maps on Earth? GPS. And these GPS have coordinates, longitude and latitude. And with GPS, you can lift your manifold to the map. And the function, the temperature change function, can be represented as a function not defined on Earth, but on the map. So it maps real numbers to real number. And that's what we see in the directional derivative. So we use standard math to compute directional derivative. And when we change only one coordinate, it's the basis vector. Change another coordinate, it's another basis vector. And they're not collinear. And derivatives can be combined in linear way. That's why it's basis. What is special for cotangent vector and cotangent space basis? We need to follow the identity. If we have one tangent vector and we need another cotangent vector that is basis in use in the cotangent space, the inner product should be Dirac delta function. So only when numbers coincide we have 1 and 0 otherwise. So the basis in tangent space uniquely defines the basis in cotangent space. So what's special in flat geometry of Rn? The complicated stuff we discuss about differential geometry and so on is collapsed into points and vectors that can be interchanged. We can compute inner product, and things seem to be simple. Actually, this special case is obtained when we set manifold to be Rn, just numbers. We take a chart that takes eth number for the point, so it's our chart, and we set the metric tensor that we'll discuss a bit later to be constant and to be the identity matrix. In this way, we appear that points and tangent vectors just look the same, but they are not the same. And what we have is, for example, flat R2 geometry. Metric tensor we choose is the identity, and the inner product is the inner product what we got used to. However, the metric tensor that's in between, it's still tensor field, but it's the constant tensor field, and it still maps two tangent vectors to a real number. Actually, the above way to illustrate metric tensor is not correct, because you see it's row, it's column, and why on earth it's row and column? It's just vector. This metric notation is really confusing, and metric tensor is better to think of as a function of two arguments. And besides, the sphere has constant curvature. In different parameterization, it can have different and changing metric tensor. And metric tensor in the parameterization where we map all the points of the sphere on the plane is changing. And if we compute the determinant of the metric tensor for this particular sphere projection, we see this picture. It's changing, it's not constant. However, sphere has constant curvature. And metric tensor has something to do with curvature, but not in this way. And this will be out of scope of our talk. Another thing that is really confusing in Euclidean geometry is vector transport. But before that, you all have nose, and imagine you're traveling along the equator and your nose points to the North Pole, right? If we go along the equator and look at the North Pole, go to the point C, your nose still pointing to the North Pole. Alright. But it was the arbitrary way to travel along some curve from point A to point C. We could go the other way. For example, from point A, then point B, and then point C. So you took a longer path. And besides you appear at the same point, point C, your nose is now not points the north, it points east instead. And that's the big difference, because in Euclidean space we just don't see that effect. But to understand this movement, this change of directions, we need to know what nabla is. Nabla is differential operator. It's not rocket science, it's just the multivariate version of derivative. So let's go to parallel transport. Nose is the same as tangent vector, and when you move along the curve, your nose change its position and its direction smoothly, right? And what is smoothly in formally way? So let's move to parallel transport. And your nose is the same as tangent vector. It points somewhere. And informally, parallel transport is the smooth change of your nose position and direction along the curve. And formally, the tangent vector doesn't change in the first approximation. So let's move to parallel transport. And nose is the same of tangent vector. And informally, parallel transport is the smooth change of your nose while we move along the curve. But formally, nabla, the differential of so we get to parallel transport. And your nose is the same as the tangent vector. And informally, parallel transport is the smooth change of your nose direction, the change of tangent vector along some curve. But formally, differential of a vector at each point in the direction of the movement is 0. It appears that this map of nose positions between points is linear. But formally it looks weird formally, but let's move to parallel transport itself. So your nose is the same as tangent vector. And informally, parallel transport is the process, the instruction to move your nose so let's move to parallel transport itself. Nose is the same as tangent vector, and informally, parallel transport is an instruction how to change the nose direction traveling along the curve from one point to another point. So let's move to parallel transport itself. And nose is the same as tangent vector. Informally, parallel transport is a smooth change of nose direction while we move along the curve. What does it mean formally? It's the So let's move to parallel transport itself. And your nose is the same as tangent vector. Informally, parallel transport is the way to move the vector or your nose along the curve smoothly. Formally, the differential of vector at each point of the curve at the direction of movement should be 0. The next thing we should remember, and it can be so let's talk about parallel transport itself. Your nose is the same as tangent vector. Informally, parallel transport is the process to move a vector along the curve smoothly. Formally, the differential of this vector at each point in the direction of movement should be 0. When we consider 2 points, gamma t0 and gamma t1, the map between vectors at this tangent space and another tangent space is linear, and it's useful for calculations. The special case when the So let's talk about parallel transport itself. Your nose is the same as tangent vector. It points somewhere. Informally, parallel transport is the way to move a vector along the curve smoothly. Formally, it is written as differential of a vector in some direction at the point, and this differential should be 0, so the vector doesn't change. If we consider 2 points, gamma t0 and gamma t1, the map between two vectors at this tangent space and this tangent space is linear. So given any vector in this tangent space, we can say what is the vector after it's been parallel transported to this point. And the linearity of this map is useful in calculations. There is a special case when the curve is that constructed that the direction of movement doesn't change Let's talk about parallel transport itself. So your nose is the same as tangent vector, and informally, parallel transport is moving vector along the curve smoothly. And formally, the differential of the vector field Let's talk about parallel transport itself. And your nose is the same as tangent vector. Informally, parallel transport is moving a vector along the curve smoothly. And formally, the differential of the vector along the curve in the direction of movement should be 0. If we consider 2 points, gamma t0 and gamma t1, and want to find the connection between vectors at the first point and parallel transported to the next point, we need to find the map between two tangent spaces. And this map appears to be linear, whichever path you choose. The linearity of this map is useful in calculations. there exist special case curves, such gammas, where the direction of movement is not changed while we move along the curve, and these curves are called geodesic curves, and the equation that has nabla and the velocities of the curve is called geodesic equation. This geodesic equation describes the condition which should be satisfied for straight lines. So in previous example with sphere, we could travel along the sphere from point A to point C in many ways, but the path along the equator was the shortest, and it's called geodesic path. And the geodesic equation can be understood as follows. Newton said, an object at rest stays at rest, and an object in motion stays in motion with the same speed and in the same direction unless acted upon an unbalanced force. So we see that a straight line is that line that is constructed by an object that moves and keeps the same direction every time. And the geodesic equation is exactly about keeping the same direction for the whole time of travel. There are many examples of straight lines that doesn't seem that straight. One of examples is Lie group of transformations. So if we want to interpolate between two pictures, this one and the rotated one, we may use just linear interpolation between two pictures, but it doesn't make sense. Instead, we better use the rotations and rotate the picture in a smooth way. That is the shortest path between two pictures, in the sense that we think it's the shortest, and it does make sense. Another example is from general relativity theory. When you drop a ball and it falls the floor, accelerating, but actually we don't apply any extra force except of gravity, but gravity is not really the force, it's intrinsic to the system, and this accelerating ball moves straight with the same speed in the same direction. So geodesic curves are straight lines because they follow the geodesic equation. Now we are ready to understand what is exponential map. Given geodesic equation, we get special class curves called geodesic curves. And this differential equation can be solved for some initial conditions. For example, given gamma 0 equal to x, the initial direction, the initial velocity equal to v, they of course belong to the manifold and tangent space of x accordingly, we get the unique solution. We get unique curve starting at x with velocity v, and we can work with this curve because it's unique and it's well defined. If we take a point, initial direction, construct our geodesic curve out of these equations, and travel along this curve for time period 1, we get a new point. And this new point is called exponential map. Now we are ready to go to optimization and see how these methods are applied in Riemannian Adam. And it will be the third video in this series.